Hello and welcome to class number 36 of Physics 218. Last time we talked about tunneling through a potential energy barrier. Today we're going to begin switching gears. We've wrapped up pretty much all of what we're going to do in developing the theory of 1D quantum mechanics in a good bit of detail. Now we're going to turn towards applications, namely to atoms and nuclei. We'll begin today by talking a little bit about atomic spectra, the experimental probe by which we've gained a lot of insight into atomic structure. We will then begin talking about the Bohr model of the atom and how the Bohr model explains atomic spectra. And then we'll begin our discussion of the Bohr model of the hydrogen atom. Now, as I mentioned, I think in the last class, a lot of what Bohr proposes is not actually physically correct, yet it's still useful for making predictions and is a good starting point for thinking about more detailed treatments of atoms. So when we come back on Friday, we'll wrap up the Bohr atom and then say a few things about quantum mechanics in 3D so that we can, next Monday, take a little bit of a short look at the Schrödinger quantum mechanical treatment of hydrogen. So I'd like to begin by looking at some slides on my computer about atomic spectra. There are some pictures that I cannot draw on the board. Okay, so a few words about atomic spectra. So there are two main types, emission spectra and absorption spectra. Emission spectra we can actually do if you've taken Astro or maybe LA'd for Astro. Oftentimes they have people look at those. You can actually do it using equipment that's in the bins in 206, 208. The common way you get an emission spectrum is you have these glass tubes filled with some gas, so something like hydrogen gas, and then you have electrodes on either end of the tube that you apply a voltage across. So the atoms inside the tube get excited in a way that I'll talk more about later. And as you can see, there's this light that's glowing from the tube. If you put that light through a spectrograph or a spectrometer, so something that's either based on a prism or more commonly a diffraction grating, what you see is discrete lines, right? You get these discrete colors different that are in the light that is emitted by the atoms inside my tube. The other kind of spectrum that I can get is an absorption spectrum. How you get that is that you take white light, and then you shine it through a sample chamber that has some of the gas that you're interested in. Once again, that light reflects typically off a grating, which separates light into components of different wavelengths. So because you're using white light coming in, you get most of the colors in the absorption spectrum, except for ones where there's an absence of light. So in absorption, there are dark lines that are missing, presumably because the atoms inside this sample chamber absorbed light of those wavelengths. So let's compare absorption versus emission spectra. So you notice that there are bright lines in emission and dark lines in absorption, like we just said. Notice that all of the lines that are present in the absorption spectrum are also present in the emission spectrum. So like this one here, this dark one to that purple one there, and vice versa. However, there are a bunch of lines that are present in the emission spectrum that are not present in the absorption spectrum. Whatever model we come up with to try to explain spectra needs to be able to explain this fact that there are lines in emission that you don't see in absorption. So you probably learned in, say, high school chemistry about the structure of the atom and how atoms consist of a positively charged nucleus surrounded by negatively charged electrons. Bohr's model of the atom says that the electrons in atoms can only exist in certain allowed orbits, so orbits of a particular radius. There are a couple of properties of these orbits, namely, these orbits, first of all, have discrete energies. The second and somewhat more radical thing is that Bohr postulated that these orbits are stable, meaning that an electron in an allowed orbit doesn't lose energy. Are stable. Now, to recognize why this is a pretty big logical leap, we need to think a little bit about moving charges. And so let's pause and do a short clicker question now. Hopefully you recognized that a charged particle going in a circle is in fact accelerating because its velocity is changing direction. Why this is a problem classically is the following. Accelerating charges, it turns out, radiate electromagnetic fields which transport energy. So let's just say accelerating charges Now, if you perhaps can persuade us to teach a super advanced E&M for 470 sometime, we might be able to talk about in detail radiation due to antennas and accelerating charges, but we'll sort of have to just take that on faith. If you're really curious, I can link you to a PhET simulation where you can wiggle a charge around and look at the electromagnetic fields that accelerating charge produces. So this is the problem classically, that a charge moving around in an orbit would lose energy, but Bohr postulates that that doesn't happen, and that these allowed orbits are stable. The second part of the Bohr model of the atom and how it explains spectra is some postulates about how you can have transitions for an electron between different allowed orbits. So there are a couple of ways. The first way that an electron can transition between orbits is by absorbing or emitting a photon whose energy is equal to the energy difference between the orbits. Photon with energy, and I'll just abbreviate energy with E, equal to energy diff between two orbits. Right. So this now starts to explain, right, why you have discrete spectral lines, right? Because, right, those spectral lines correspond to photons of a particular frequency, and you know that from Einstein that E equals h nu for a photon. So those spectral lines correspond to the energy difference between two particular orbits. The second way that you can have transition between orbits is by having atoms that are excited via collisions. Namely, due to absorbing in collisions. So the best example of this sort of thing is those spectral emission tubes, like what I showed you on the emission spectrum slide at the beginning of the class. Right. So those tubes really consist of a glass tube filled with gas, and there are electrodes at either end of the tube, and you apply a voltage across those electrodes. That voltage causes charges to you sort of have a little bit of ionization. You start to get some charges that can flow, and then those moving charges give rise to collisions between the atoms in the gas tube, and that's why that's how you get atoms excited, or they absorb energy up to higher levels, and then by dropping down to lower levels, they can emit photons. That's how you get emission spectra from a tube. One remark here, right? So note that for emission spectra, and this is the reason why there are some lines missing in emission spectra, in absorption spectra that you see in emission spectra. So normally atoms mostly in the ground state or the lowest energy orbit so in a hypothetical energy level diagram, so let's call this n equals 1, n equals 3, right? So in an absorption spectrum, right, you would see transitions corresponding to the following, right? So going from 1 to 2, or from 1 to 3. So these are seen in absorption however, what you don't see is the following. You don't see this absorption, and I'm going to cross that out, right? Because most of your atoms, or nearly all of them, are in this ground state. Very few are in the n equals 2 state to begin with. Now, this isn't a problem for emission spectra because the process of having atomic collisions manages to excite the electrons to higher energy levels. So in an emission spectrum, you can perfectly well see a transition that begins at a level higher than the ground state. So this explains why absorption spectrum has fewer lines than an emission spectrum. Let's now go and have you just do a little exercise thinking about what we've learned about the Bohr model of the atom and how it relates to spectra. A pressing experiment, theoretical challenge at around the turn of the 20th century was to try to understand atomic spectra. And Niels Bohr was able to use a mixture of classical physics and some early quantum ideas to predict the hydrogen spectrum. We're going to start to follow some of that logic today. We'll focus for today on being able to predict the radii of the allowed orbits. And then when we come back on Friday, we'll sort of close the loop and finish predicting what the spectrum would be. So hydrogen, as you may know, is a proton and an electron. I'm going to now ask you to think a little bit about how this might work using physics you've seen before in 117 and 118. So we'll do a whiteboard exercise now, and when we come back in part 2 of this video, we'll look at that exercise and think about what the implications are for the allowed radii.